All right, in this final section on this polymers unit, we're going to talk about condensation polymers. In condensation polymerization, a small molecule such as water, NH3 or HCl is released for each extension of the polymer chain. So we remove or we release H2O, NH3, HCl in order to combine monomers together, in order to extend and continue adding monomers. Each extension results in the formation of a dimer, which can undergo further condensation polymerization reactions as it has a reactive group at both ends. The reactions terminate when a monomer with only one reactive group is added and no more extensions are possible. Dehydration synthesis is a subset of this class of reactions, where a water molecule is formed for each extension. You can see in earlier sections of this presentation in detail dehydration synthesis where that happens. A condensation polymerization reaction forms nylon, a copolymer that contains a combination of two different types of monomers. Hexamethylenediamine and adipic acid react by splitting out a water molecule to form a carbon-nitrogen bond. The dimer formed has an amino group at one end and a carboxyl group at the other. This enables it to undergo further condensation polymerization reactions as it has two reactive ends. Examples of condensation polymerization reactions include resins, such as Urea formaldehyde and Phenol formaldehyde, and synthetic fibers, such as nylon and terylene. We discussed on the previous slide the process of nylon formation. Let's review it in detail in the coming slides. So here's that reaction of hexamethylenediamine and adipic acid. Nylon 66 is a polyamide fiber. Each monomer unit has 6 carbon atoms in it. It is used in textile fibers, sheets, and bristles for brushes. So on the left here is hexamethylenediamine. There's 6 carbons, and on either end are these 2 nitrogen groups, these amine groups. And then on the right here, as a second reactant, is this adipic acid, which has 4 carbons in the middle, and then on either end we have 2 carbons double bonded to oxygen and then OH groups. So we're going to remove water. So on one of the amine groups, we'll remove a hydrogen, and on one of the carboxylic acids, we'll remove the OH group. And in doing so, now the nitrogen will be bonded to the carbon. So in this product, we have nitrogen bonded to carbon with the removal of water. And this is nylon 66. Now, if you notice here, we still have an amine group on one end and this carboxylic acid group on the other end, so that we could continue adding more and more monomers to make this polymer structure even larger. All right, let's talk about something maybe we've heard of, polyester. Dacron or terylene is the commercial name for polyethylene terephthalate, PET or PET. It is a copolymer formed from the condensation reaction of ethylene glycol, which is a dialcohol, and p-terephthalic acid, a a dicarboxylic acid. So a dialcohol, ethylene glycol, would have 2 OH groups. A dicarboxylic acid would have 2 COOH groups. It is called polyester because the reaction involves a carboxylic acid and an alcohol forming an ester group. So we have many esters formed, so polyester. It is used to make a fabric which is crease resistant, durable, and not easily damaged by pets. It is also used as a substrate for solar cells and for waterproofing undersea cables. This shows the reaction that forms polyester. As one reactant, we have ethylene glycol, and as our other reactant, we have terphthalic acid. The ethylene glycol, because of the dialcohol, has an OH group, and the terphthalic acid, because it's a dicarboxylic acid, has a free hydrogen that it can give up. So if we remove these through that condensation reaction, we remove the water, we'll form a bond then between this terminal carbon here and the carbon, the COO, C double bond O carbon, okay? So that's what we see right here. This bond right here is the bond that is combining the ethylene glycol and the terphthalic acid. And that's our polyethylene terphthalate, PET, or polyester. So this OH on this end and this H on the other end, the OH and the H outside that box, can continue to react and form that water molecule at each extension point of the polymer, allowing the chain to continue. Urea formaldehyde resins. Urea reacts with formaldehyde to form a type of resin which is used in molded plastics. A space network polymer is eventually formed. A space network polymer has cross-linked polymer chains, a three-dimensional interconnected framework. Condensation occurs at various stages of heat treatment during the polymerization. First, form a monomer. 3 monomers then combine to form a trimer. Finally, trimers can then combine with glycol to form the network polymer. All right, so let's show each of these steps separately. First, we combine the urea and the formaldehyde to form a monomer. And the monomer unit looks like this. And you can see from the shading that on one end we have our OH, and on the other we have a free hydrogen. So this monomer here can continue to the next step. All right, step 2, after we form that monomer, you see here's one monomer. These 3 monomer units condense together to give a cyclic trimer unit, which is pictured on the right. So we have a cyclic trimer unit, each with a protruding NH2 group that can be the next point of condensation reaction with glycol molecules. All right, so step 3 is forming the network polymer. So we have our trimer, which we saw in the previous slide, the formation of this trimer. We have some large number of them, n number of them, right? And our formaldehyde that can combine. So remember, we have these free nitrogen groups at each tip of this trimer, where the formaldehyde can react and attach. You can see it right here. See how where this NH2 was. Now we have the C double bond O, and then here's the NH2, the formaldehyde here with these dashed lines. So the cyclic trimer condenses with more formaldehyde at each NH2 to form a network space packing polymer, similar to melamine. The result, or the product here, is a powdered resin, which you can see right here, that can be used for a wide variety of uses. It's used in foam insulation, furniture, resin, and all of these objects, different resin objects that are shown. Let's talk about phenol formaldehyde resins like bakelite. It is a condensation polymer formed from phenol, which you see on the left here, and formaldehyde here. And you can see the polymer resin structure here, where you have the CH2 groups surrounding the phenol, much like in that trimer structure that we saw previously. Resins with a low degree of polymerization are used in bonding sheets of paper, cloth, plywood, etc. Bakelite is used in electrical goods and special tabletops. Melamine and formaldehyde resins are used in making unbreakable cups and plates. There are some other properties of polymers. A polymer's resistance to chemical attack is not dependent on its chain length. The following characteristics of polymers are not based on molar mass. They're not dependent on size. Polymers, regardless of size, have characteristics of color, refractive index, hardness, density, and electrical conductivity. Certain high polymers can be molded and suitably shaped under high temperature and pressure. These high polymers are known as plastics. They're generally tough and resistant to acids and bases. Thermoplastic plastic or polymers are linear polymers which are soluble in many solvents and which soften on heating and become hard on cooling. This process can be repeated, and these substances can be melted again after they've been molded as desired. Examples include cellulose nitrate, cellulose acetate, polyethylene, and PVC. We saw examples of that previously when we're talking about polyethylene and PVC. You can review those slides about like blown plastics back in the previous section if it interests you. All right, let's talk more about these moldable polymers or plastics. Thermosetting plastics, or thermo meaning temperature, right? So plastics that can set and harden once they're cooled. They're three-dimensional polymers which are insoluble in any kind of solvent. These polymers cannot be softened again after being molded into a shape under high temperature and pressure. Heating after setting just results in decomposition of the polymer. Examples include the bakelite that we saw before and the urea formaldehyde resins that we saw before. So how do we modify polymer behavior? The arrangement of these polymer chains significantly affect the properties of a polymer. For example, polystyrene, which is constructed from the monomer styrene, process you can review in detail in the previous slides, is brittle in its pure form. But polystyrene-based polymers are actually copolymers of styrene and butadiene. So here's an example of a polystyrene-based product. Acrylonitrile butadiene styrene, or ABS, is a tough, hard, chemically resistant plastic produced by the copolymerization of three monomers. acrylonitrile, styrene, and butadiene. Okay? We get ABS, much harder, more chemically resistant plastic. Much different from just the polystyrene, pure polystyrene that we reviewed earlier. So if we make these copolymers that include other things, we can make an even stronger plastic product.